Good morning from here in London. Thank you for joining us for today's webinar with a focus on chemical process industries. Today's topic, we'll be looking at improving operations, coupling DEM and CFD to optimize particulate flows. We are delighted to have two speakers for you today. We have Dr. Ravindra Aglave, who's the Director of Chemical and Process Industries here at Siemens PLM Software. And we also have Ole Baran, PhD, who's an application specialist. I'll just give their bios and then we'll get things kicked off. Ravi, as I said, is the Director of Chemical and Process Industries here at Siemens PLM Software. All throughout his career, he has performed advanced engineering backed by CFD and simulation. He leads the effort of applying CFD for chemical processing applications. And for Ole, after obtaining his PhD in physics from McGill University, Ole carried out postdoctoral work developing computational models for 3D granular systems. Since he entered the CAE market around 2007, he has performed engineering consulting on DEM-related projects for industry and government research organizations. Okay, so without further ado, I would like to kick things off by passing over to your first speaker today, Dr. Ravindra Aglave.
Thank you, Jay, and welcome everyone to today's webinar, which is on improving operations in particulate flows, especially using DEM and CFD in a coupled manner. But in general, I want to give you an outline for today's webinar. We are going to go through quickly an introduction and the methods for modeling particulate flows. Since it is particulate flows, we are going to take a look at both the traditional Lagrangian tracking methods as well as the discrete element methods. And then I will pass on the ball to my colleague Ole, who is going to talk about material characterization and perform a demonstration for you for a coating simulation. And then in the end, we will have a short summary and conclusion followed by question and answer session. So as you may be well familiar, particulate flows are found in various different unit operations in the chemical and process industries. Some of them are listed here, like calciners and roasters, cyclone separators, spouted beds, fluidized beds, and so forth. And some of them also include solid-liquid type of applications. For any of these unit operations, there are always challenges in achieving objectives, and mostly they are related to how to maximize efficiency, how to maximize distribution, how to minimize energy consumption, how to avoid excessive wear and abrasion in those equipment, which ultimately leads for one to say that we want to optimize overall performance at the complete system level, and there are always counteracting parameters. And these systems may have a single or multiple objectives, and the multiple designs that one needs to explore, one can obviously do this experimentally with trial and error, or doing multiple simulations one after the other. The challenges in performing simulations generally mean that if you spend too much time trying to just build your model, then there is very little time that is left to explore and assess the results and find a good engineering solution. So ideally, what one would like is that the engineering time is in line with where one finds more value, that is exploring designs, exploring operating conditions, assessing them, and then finally finding the solutions. Therefore, we need to think about how our engineering time can be used in a similar fashion. Now, if you're already using simulation, be it fluid flow or specifically particulate flows, which is what our topic for today is, then simulations are generally used by many companies to validate a given design or troubleshoot something that is not operating properly, and in many cases also to predict the changes in performance if you make a change in operating condition. However, really cutting-edge and innovative companies try to automate their simulation workflow and then use intelligent search algorithms to really explore the best designs or the best operating conditions so that they can find these optimum conditions fast. And when we talk about modeling particulate flows, there generally are quite a few different methods. We are only going to focus on the two important ones here today. The first one being when we track the particles, which are generally lean particulate flows, and we do this to predict the effect of turbulence on particle dispersions, and perhaps contact mechanics is less important. The other complementary method for dense type of particulate flows is the discrete element method, where granular flow properties such as jamming and shearing could be important. And we're going to take a look at examples and case studies for both of these types of flows. So a typical lean particle flows could be in a cyclone separator. One validation example is shown here, where particles are entering the cyclone at a certain velocity, have a certain density, and then one is worried about how much pressure drop is encountered, but also what is the separation efficiency of these particles. Here is one quick case study that shows that how simulation was used specifically for validating the design and troubleshooting the design. It comes from the coal milling projects as a courtesy of the coal milling projects and Aerotherm. The challenge here was how to maximize the throughput of a pulverized coal to burners and reduce pressure drop through these rotating throats as well as static classifiers. In this case, star CCM Plus was used to optimize the flow through the rotating throat and the classifier by making geometric changes so that a reduction in air velocity is achieved, as well as a more uniform air distribution in the grinding area can be achieved. The result in multiple projects was seen, and typically it meant lowering of the operating cost of the fans that are used, as well as reducing the wear in these equipment. In one case, 21% average throughput improvement. In another case, maximum throughput increased from 22 to 30 tons per hour. So this is a classic example where simulation was used to validate a new design or troubleshoot an existing problem to improve it. A second example comes here, which is for a series of cyclone separators in a plant where erosion was a major problem in the flow containing the particles. And so going from the original design to a modified design, it was observed that a 30% reduction in the erosion could be achieved, resulting in significant savings in maintenance cost. This again is an example thanks to ArcelorMittal and Aerotherm. This is a classic case where simulation was used in the troubleshooting mode for a given problem. Now let us take a look at some of the dense particle flows where discrete element modeling can be used. And generally, discrete element modeling can resolve the contact physics in much detail. A few simple validation examples where things such as rebound angle and impact angles are calculated and compared with analytical solutions. And we see that this type of method is a lot more accurate in predicting the contact mechanics. Obviously, then, this method is very suitable to be coupled with a CFD simulation where flow of fluid and flow of particles using discrete element methods can be used together. An example here showing how the pressure drop per unit length is varying with a varying unit fluid inlet velocity. And then if you're looking at the pneumatic conveying systems, these are the systems that essentially allows to connect any 2 points for particle transport in the shortest possible path, where toxic and hygroscopic particles can be very classically eliminated from the rest of the system. Traditionally, the air side only pressure drop is calculated using typical correlations or formulas. However, the trouble with such a calculation is that there is significant amount of pressure drop that is realized because of the particles that are present, especially which depends on the shape and the size of the particles, as well as air velocity and temperature. So from the entrance to the end of this system, there is a slip velocity that changes with the air velocity as well as the particle velocity as they are accelerated in the acceleration length. So if you ignore the pressure drop that is calculated due to the varying slip velocity, one might end up designing these systems with higher power than that is necessary. In such situations, DEM can provide data for such complex geometries as well as accounting for the dense particles that are flowing through the system. And this is showing you then a simple animation where a pneumatic system can be simulated, and you can use this irrespective of whether the flow is dense or lean, and also investigate if there are the chances of a pulsating flow behavior that may be caused, which can influence the stability of the system. Let us now look at another example, which is for a dense spouted bed. Here is a very simple validation where we see a fluid being injected from the bottom and simulation being carried out in a coupled manner between CFD and DEM. The leftmost picture is showing you an image from literature where some experimental data is reported, and the right two images are showing you two different simulations, one done using what is called as a coarse grain method and the other done with using all the possible particles that are in the system. And then we are comparing the power spectral density versus the frequency charts, and we see that simulations are able to reproduce the experimental data with a good amount of accuracy. So that gives us the confidence in predicting what would happen under various flow conditions to predict the behavior of the system. Obviously, this type of simulation can also be used to investigate if we are having a fluid that is used to coat the particles. So one can begin with looking at a single particle simulation to analyze the efficiency of the coating or the fluid film coverage over the particle, which is shown here in the next slide for either spherical or tablet-shaped biconvex particles. And once it is known that what is the efficiency for coating of a single particle, one can then use this information in a complete system simulation, whether it be in a rotary drum-type coater where we are looking at comparison of a single spray versus two sprays and how does that affect the standard deviation of coating, which is shown here in the left animation. And obviously what we see is that the two sprays is much more efficient and has a lower standard deviation of coating thickness. In a similar manner, one can also investigate unit operations like a Worcester coater, where you have again a gas that is injected from the bottom to fluidize the particles. All the details of the geometry are given in this slide, and then we look at how the coating distribution is changing with time, and this distribution is again animated in the right side of the animation, where we start to see that as time progresses, the coating distribution then starts to change as well. So starting from a very simple single particle coating model and using the information in a more complex geometry or a complete system, simulation gives one the ability to be able to predict the distribution of coating depending on the geometry and other material properties that are involved in this system. This is an example of a tablet manufacturing process in which the compaction of powder for tablet manufacturing is seen, where again CFD is coupled with DEM in a single environment, and one needs to consider the flow of fluid because modeling the dye with a suction pressure at the bottom with powder filling from the feeder sliding at the top of the surface is extremely important to get accurate results. And this virtual methodology then enables one to optimize the process with much lower amount of investment. And then it also enables one to have the boundary phase interaction, which restrict the particle flow beyond the dye bottom surface, which was or which would have been otherwise not possible if one could not couple the CFD simulation with the DEM simulation in a single environment. Here is another example where simulation was used more in a predictive manner. So this is a machine that is used to separate heavier solids such as stones from lighter solids such as wood chips based on the density difference. So you see that the mass flow of air coming from here, and because of the segregation that occurs due to differences in density, the heavier material is supposed to fall down from here. And so those particles are represented with different shapes. The lower figure is showing you the flow of air and how it splits between the two exits. And what was observed was that the rejection of wood and stones that was expected and that is found from the simulation matches very closely with each other. And how this enables engineering is that once this sort of test is done on a bench scale unit, then this information can be used to scale up to design units that are much higher in capacity without having to do additional or further experiments, but still maintain the quality of separation that is required in this equipment. Let us take a look at one more example, which is for a hopper design. Hoppers are used in particle processing in many different industries. One such example is shown here on the left. And it is known that if you have particles of two different sizes, then they will segregate as they pass through such hoppers. In this case, obviously a correlation with the bulk flow behavior of the particles was established using the discrete element method so that the particle properties match the bulk flow behavior correctly. And then as a result, various different designs were explored to find out which design will give the minimum possible separation. And why is it so important to have minimum possible separation? So for example, in the pharmaceutical industry, the drug substance which is used, if it is not distributed uniformly, then one has to add extra drug substance to make up for the segregation or the separation that is seen. With the use of simulation, then one is able to scale up these systems in such a way that the design has minimum possible separation of particles. And as a result, almost up to $1 million of savings could be realized when developing the large-scale system. So you can see the impact of using simulation in such a complex system where simulation was used not only in validating the design, but also in the scale-up phase. Now, we are going to take a look at how to do material characterization of the particulates, and then look at a demonstration and an example of how design space exploration can be used for a coating simulation. And for that, I'm going to pass on the ball to my colleague, Ole Baran.
Thank you. So I will continue discussion of DEM in Star CCM Plus. And my first topic will be material characterizations, and calibration of DEM. So whenever we are setting a DEM model in CCM Plus or any other software for that matter, we need to specify the information about the particle level properties, the parameters such as static friction, rolling friction, restitution, Young modulus, coarse grain particle size, and at least can be longer depending on what particular particle level physics we activated in our project. And then immediately there is a need to calibrate those values so that the difference in the behavior of the collections of many particles would be minimized compared to the real-world behavior of granular materials. For example, we have here the particle settled at certain angle of repose, the angle between the surface of particles and the horizontal in the DEM model, and on the left we have the real-world behavior of settling particles. And there are several methods out there for calibrating DEM models, and I just wanted to show you an example of one such calibration methodology that was recently developed at Purdue University, and here's a reference to the Harshranjan work methodology for DEM parameter calibrations, which he did using DEM in CCM Plus. So this particular method suggests 4 stages of the process. The first, we have to characterize, do the material characterization experiments and get the basic particle properties like a density and particle size for the DEM model. We can then do some initial assumption approximations that will keep in mind that we want to simulate the particular flow regime and particular number of particles in a reasonable time. So we don't want for it to take too long. So there would be some approximation on the size of the particles and the stiffness of the particles set at this point. And then the next level is to do the calibration of the frictional parameters such as static friction, rolling friction, and so on. And within this suggested method, one should do the lab experiments for the angle of repose test and the shear cell test and simulate them and try to do find the input parameters such that have the same such a simulation will reproduce as close as possible the experimental results. And once we've done that, we should do the calibration of Young models using uniaxial compression test simulation, and then we are ready to validate our process, our results, or use the model in the real applications. So here's our example of how it was done by calibrating simple granular materials such as Ottawa sand or glass beads. So dynamic drained angle of repose test was first done experimentally. Particles are set first at the top part of the device, and the gate is opened, and they all fell down and forms some kind of static pile with a surface angle with horizontal, which we call the angle of repose. And then we try different values of friction, rolling friction, and static friction to find which one provides, in the simulation, which one provides the same angle of repose in experiments. Same goes for the shear cell test. The top view here is the experimental view of the experimental device, and bottom is a snapshot from the simulations. And then we find many values of the rolling friction and sliding and static friction, which could provide the same bulk state of materials in the simulation. So we see the green line corresponds here to the shear cell test, and the red line corresponds to the results of the angle of repose test. And then whenever they cross, that means it is the place where both tests provide the same reproduce correctly both results, angle of repose in the first test and the stress as a function of the strain in the second test. And then the next step would be to fine-tune the Young modulus or stiffness of particles by doing the uniaxial compression test and running the simulation in your actual applications. So this was kind of optimizing the DEM input model parameters. We call it calibration. So the next part of my presentation would be about optimizing. Once we have this calibrated models, we can run it in the real equipment, and we can do different types of optimization. Optimize the equipment which is used to which is used to have particles in it, in simulations that simulate the processing of particles in this equipment. So I'm going to do through the next 20 minutes. I'm going to go through the settings of the simple demo, starting from the simple geometry. I will go through setting the physics and running the simulation of coding the tablets. And I'll show how to use CCM Plus to efficiently generate a virtual prototype and get insight into mixing and coding performance, how to quickly and easily generate, test, and compare design variants, and automatically and intelligently search the design space to find better design faster. Let me switch to the CCM Plus Windows software. So you see right now on the screen the typical layout in the CCM Plus. In the middle, we see the view window, model view window, where I have the geometry already preset for this demonstration. We see the the particle coder, which is a rotating drum, which has some baffles inside that's supposed to help mix the particles. On the left, we have the panel that helps to set up the physics of the simulated process. At the bottom, we have the panel where we set the parameters of the model. And the right, we have DEM simulation assistance, which should be used whenever we set up the physics that involves DEM particles. So this geometry is already pre-meshed, but nothing else is set. So we're going to go from this stage to the end when the particles are being introduced and simulated. The geometry was created in the 3D CAD CCM Plus software. So we have several design parameters, such as, for example, baffle height, baffle twist angle, and number of baffles. And we can very easily change any of those design baffles. For example, right now we have 4 baffles, which means 4 baffles on the right side of the drum, and the 4 symmetrical and shifted baffles on the left-hand side. Let's change it to the value of 12 and hit the remesh button. The CCM Plus will remesh our currently geometry, and you see you have many more baffles. So we change design very easily and simple in this way. Let me go back to the original 4 baffles in this particular geometry. It will be our baseline design, and we will be looking for the way how to optimize design to maximize the process of coating particles inside that rotating drum. By the way, the motion of this drum is already set, it will be rotated at 10 RPM. So the first thing to set the physics, we have to define DEM phases. For that part, I will let me call load the simulation assistant. On the right, so for that part, I'll use the DEM phase part of simulation assistant. I'll just click it, and it will set up the DEM physics for me in Star CCM Plus. It's in a single click. It activates all the relevant for DEM models in Star CCM Plus. So on that model tree on the left, we have discrete element model activated. I would notice that it reported that it used some default values of material parameters. I noticed the density is too high. I would like to change the density of particles to something more reasonable for this case, like 1,500 kilograms per meter cubed. Same way I can change any property of particles like a stiffness, Poisson ratio, and so on. The next step I would do is, I know that each particle has to carry information about the amount of coating it has, so I would activate the model for Lagrangian passive scalar, which would allow to keep the information about this coating, amount of coating on each particles which we're moving throughout the coder. So I from the optional models, I select the passive scalar model. I'll close it. So now in the list of models, I see the passive scalar model, and I create a new passive scalar, which I will rename to the name coating. That's all. That's how easy it is to create any custom property per each particles. Finally, I want to not to use, by default, the simulation assistant offered me the spherical particles. I would like to use, for example, other shape of particles. In this case, I will use the cylindrical particles. I have the choice of preset shapes available from this menu. Now I want to add another solid phase, which will be droplets. Those are particles that are sprayed on the top of the rotating cylindrical particles. So I will call it droplet. Click OK, and now I have two DEM phases defined in Star CCM Plus. I am okay to use the spherical particle for the droplet phase. What I noticed that the material name is catalyst. I will replace with more, for example, syrup. I will spray particles with a syrup in this case. And material properties, it learned that I liked the 1500 more, but I will use some other density for these particles. Again, it would depend on the density of real fluid that is being sprayed on the top of rotating particles. And same as before, I would like to activate the passive scalar model so it will carry information about the spraying fluid on those droplet particles. Also, I would like to activate partial depletion model. So the moment the particle impact on the cylindrical, the moment the droplet impact on cylindrical particles, it will be deleted. It did the functions. It coated the particles. Doesn't need to exist anymore in the simulation domain. So we have passive scalar. For this new phase, we create new passive scalar, and let's rename it to spray. And we have partial depletion model, and let's say that we have to put the if statements here, so that if spray value is not 0, because it will be initialized with the value 0, but when it collides with the particles, it will get another value. So then the particle will be deleted. Otherwise, it will stay in the domain. And that concludes setting DEM physics. I will save the simulation. The next step is to set the contact physics, how the particles interact. So again, our simulation assistant will set up all their physics automatically by clicking on that link. So we see the particle separately set, particle wall, droplet wall, and droplet particles are all they use different models how to interact between two phases. So I focus on particle droplet interactions. So I want to activate the passive scalar transfer. So this passive scalar we created, they have to jump from the droplet onto the coated particles. So I activated passive scalar transfer model. And by saying which passive scalar talks to which one. Then I go to the linear spring model, and I say, for this things I set really low value of stiffness. We don't need to resolve the collisions very accurately, because the droplet will be deleted immediately once it's passed the value of the coating liquid to the particles. The next step is to set to reduce the stiffness of the cylindrical particles, or tablets we can call them. So there is a normal and tangential spring values. So by default they are quite high values, and if we reduce slightly, like for 2000, the simulation runs much faster. We're going to simulate it on my laptop computer, so we need to do some. We need to run some softer particles and less of them to have done it in the reasonable time. So we set the contact physics. The next step, we set how do we go inject the particles. Again, I click on the link of our simulation assistant, which will try to set it for me very fast, but I have to fine-tune it. For example, for injecting particles, cylindrical particles, I go to the condition of injectors and say the particle packing specification, I want to inject specific number of particles, particle count, and I said, let me inject 8,000 of the cylindrical particles that will be tumbling in rotating drum. And I specify the size here of particles, and I check that the size that the simulation assistant selected is quite good, so I left it as it is. Number of seeds, that should be more than the number of particles, so that all the particles will be injected in the first iteration, so I put it like 80,000. Particle orientation uniformly distributed, that means it will be randomly oriented when they are introduced into the simulation domain. And there is some initial velocity to help it pack at the bottom of the things of this container. So now we go to the droplets, setting for the droplets. Same thing, particle packing specification, we change to particle count. And then we set values for number of particles. Here we want to make it time dependent. We don't want to inject any droplets before the real cylindrical particles are settled at the bottom. So what I do is I use the variable time and say if it is bigger than, say, 0.22 seconds, then I will start injecting particles. Otherwise, my number of particles should be 0 in the domain. That's how we set the input to this case. And there is a specific way to set the mode of injection. If I set this injector cycle limit to 1, then the number of seeds will specify how many particles I want to have injected every time step. So I will be injecting 50 droplets every time step. Particle size, simulation assistant suggested to have size distributions. I will switch to the constant and override the value to, let's say, 4 millimeters. And I will set some initial, also I will go to this random injector for droplet top node and say that it will not be injected in the whole mixer equipment. It will be injected in the in a specific part which is called injection volume, which let me go to back to the geometry, and this was preset injection volume. It's a conical part which is a cone sprayer. So that all those droplets will be generated here and deposited into the flowing cylindrical particles bed. So final things I need to do is to change the velocity so it has a 45 degrees angle, because our spray system is in the direction. So I put the X and Z component equal. So because our spray system is located under the angle towards the surface of the surface of the particles. So having done that, I just recall that I also want to reduce the Young modulus of the droplets, because the lower Young modulus of droplets means faster simulations, and we don't need actually to resolve much the collisions between droplets and droplets, so we can have really small value in this case. So we finished setting DEM physics, DEM contact physics, and particle injection sections. Then we are almost ready to run the simulation. So I use the simulation assistant to set up the solver settings, which will enforce the use of best practices for this particular applications. I will go to the solver, increase the fluid time step slightly, as we don't want to wait too long till it solves the system with a small time step. I set up the post-processing. Again, simulation assistant will allow me to do it in just one single click. So we see now our system, our small injector inside for droplets. And I want to do two things before I start running the simulation. First, I will increase the opacity so I see the geometry more clearly. And I will remove the front, so we see inside of our coater. I remove the front wall of this from the view. And at this point, we started from basically scratch. Only geometry was prepared and set up, all the physics, DEM physics, and all the solvers. We are ready to start. So I'm running the simulation. It should inject 8,000 particles. You see, it complains that I have a typo in the word spray when I set up the passive scaler. Let me correct that typo. Physics model, Lagrangian multi-phase, Lagrangian phases, and droplet models. So you see that's I use it with Parry spray. Okay. And let's clear solution again and run the simulation with a corrected mistake. So you see there are already 8,000 tablets injected instantaneously into the simulation domain, exactly as we specified in our settings. And at some moment, when the solution time, which is shown on this corner, is 0.22, the droplets will start to be sprayed on the top surface of mixing cylindrical particles. Those particles are small cylinders, as we set up previously. As those droplets will go ballistically towards the particles, the moment they touch any of the particles, they pass the information about the coating liquid from those droplets to the particles, and each cylindrical particle will have information about how many droplets it absorbs during its existence. So basically, we will have ability to trace amount of coating on every single cylindrical particles in this case. I forgot to set up, because my laptop has 2 cores, so I can always run 2 times faster, but to do that I need to activate so-called load balancing. You see there are already droplets being injected in these conical areas, and they are going towards the particles that are settling and tumbling inside the drum, the rotating drum. Let me stop at this point the simulation. This is just a demonstration. And let me color the particles based on the amount of the coating they have. So I use right now. So you see at the moment only 1 particle is coated here because it was flying in the air through this coating area. But as the simulation progresses, there will be more, and we can control amount of the particles. So at this point, I switch back to my presentation and show how to post-process this system using our built-in Optimizing part of the software, which allows you to automatically change design, go through design space of the equipment and optimize the coding process in this case. So this is our baseline design with a baffle height being 50 millimeters, baffle twist angle 20 degrees, and number of baffles 4. And we see this already solved solution for 15,000 particles. And we trace the number of coded particles, which reflect the rate of coding for this particular design. We trace a damage index, which corresponds roughly what percentage of the particles are in the zone of have the risk of being damaged in this equipment under this flow rate. Also coding uniformity of the particles, which is calculated as a variance of the number of droplets absorbed by each cylindrical particles. So then, using the built-in Optimate option of CCM Plus, we can build new CAD, mesh it, apply the same solution and analysis, and explore many designs here. So we can change number of baffles, numbers of twist angle of baffles in all their geometry automatically and in a meaningful manner, and assess the best possible design. So when we activate this Optimate options, we set which design parameters we want to change, how many variations we want to allow, minimum, maximum, and increment values for each equipment design parameters. And we say that we want to maximize coded tablet count and minimize tablet damage index. So there are a total of 125 different design possibles with this input. But the Optimate in StarCCM Plus was smart enough to arrive at the best Optimate design, which maximizes the coding rate within the first 35 designs, by evaluating first 35 designs. And our DEM code is fast enough, so it takes about 2 hours to simulate one design on 4 cores. For this particular size of particles and particular number of particles, which is 15,000 cylindrical tablets. And here's the results of the optimization code going through all these different designs. There are 35 of them, and for each of them, it calculates the coded tablet count. So it finds starting from the baseline design, it finds the design which has a maximum value of the coding rates. It's 7,000 coded tablets, and the tablet damage index is still quite high. So let me run this new design. You see the height of the baffles and the number of baffles and the twist angle of baffles is different than the original baseline design I shown on the previous slide. But it also gives you the family of the good performance designs. For example, if you look at the design number 30 here, it gives quite a high rate of coding rate, still close to 7,000 coded particles in the first 2 revolutions, but the number of damaged particles is much less. It's actually smallest damage index. So you might want to consider that design as the best one in your simulations. So here's a summary slide. I want to say that we show how to set up the basic coding simulation in StarCCM Plus, and then how to let the Optimate options of StarCCM Plus to do the automatically design exploration and find the best values for this for the height of baffles, for the number of baffles, for the angle of baffles, which will provide the maximum coding rate and the minimum tablet particle damage in your equipment. And that concludes my demonstration. Thank you very much for attention.
Thank you, Ole. I'm just going to take a couple of minutes now to summarize. And as we go there, I want to essentially say that irrespective of whether you have dense particle flows or lean particle flows, and obviously whether they're coupled or not to fluid flows, the same methodology, that is using an automatic design change or operating condition change, remeshing, resolving, and then intelligently searching for better designs, can be applied to pretty much all examples. In this second case that we see, this is related to a cyclone, where we are varying now the diameter of the cyclone, the constriction length of the cyclone, and the inlet length of the cyclone. Particle diameters are given here, about 1.2 microns. And the animation on the next slide is essentially showing you that by varying those parameters, we are trying to find a design that maximizes the separation efficiency of the particles while trying to maintain or minimize the pressure drop. And the chart, which is on the bottom left corner, is giving you a correlation between how these design parameters, that is the cyclone constriction length, parallel length, and radius, are correlated to the efficiency and mean pressure drop. So this is a very important engineering insight that you can gain from this exercise. And then as a result, from the baseline design to the best design, what we see is that the efficiency increases from about 74% to 88%, while the mean total pressure drop is maintained more or less the same. So we can see that utilizing this automated process essentially helps you find a better operating cyclone or improve the performance of the cyclone in a very easy-to-use manner. So to conclude for today's webinar, we can simulate both lean and dense gas-solid as well as solids-only flows, and can be used to either validate designs or troubleshoot problems or even predict performances. But then automating the simulation process and exploring designs intelligently can help engineers to use the benefits of simulation, workflow and automation, intelligent search algorithms to find better solutions in a shorter time. And with that, I will conclude my portion and hand it back over to Jay.
Paul, thank you to you all. With that, the session is closed. Goodbye.